Hi everybody. Today we're going to have a look at chance and probability and how we've completed some exercises during the term. So we're going to start with likelihood. The likelihood of an event occurring can be described in a number of ways, and the typical natural language words that we use are impossible, unlikely, even, likely, and certain. Now these words are good, but they're not very precise in that look at this little graph below. Unlikely can be anywhere between here and here, or anywhere between here and here, in fact, with very unlikely down one end and unlikely at the other end. So if we're saying two things are very unlikely, one could be much more unlikely than the other. So we want something more precise than that. And in maths, we tend to use numbers for that. So we typically put probability values between 0 and 1. 0 being impossible, 1 being certain, everything else in between. You can't get more unlikely than impossible. You can't get more likely than certain. Now, we don't only represent numbers between 0 and 1 as decimals. We can also represent them as fractions or as percentages. And all of those can be probability values. Now, we calculate these numerical values by looking at either what may happen in theoretical probability or in what has happened in experimental probability. We're going to start with theoretical probability. That's always a good place to start. So what we do first is we examine the outcomes that are possible and identify the equally likely outcomes and assign them probabilities. Typically, this starts with listing the outcomes in a sample space. So this is what a sample space looks like. It starts with a letter. In this case, I've used S for sample space, a colon, and a curly bracket followed by all the outcomes that are possible. So for a dice roll, it's possible to get 1, 2, 3, 4, 5, 6. And here they are in our sample space, 1, 2, 3, 4, 5, 6. Now we could also do this for heads and tails. So we'd have S, colon, curly bracket, heads, tails, and a closed curly bracket. Now there are other ways to list a sample space, but this year that's the only one that we're focusing on. Now, if we were going to establish a numerical probability, we use this formula. So the probability of some event is equal to the number of successful outcomes divided by the number of outcomes. So for a dice roll, if we had 1, 2, 3, 4, 5, 6, probability of 2, we'd count up the number of 2s. There's 1, 2, we'd put that on the top, and we'll put the number of outcomes on the bottom. 1, 2, 3, 4, 5, 6, there it is on the bottom. If we're looking at the probability of greater than 2, we'd look at all the numbers greater than 2. So 3, 4, 5, 6, there's 4 of them, and divide it by the number of outcomes. There's 6 outcomes, it's on the bottom. And then if we wanted to, we could simplify this fraction by dividing the numerator and denominator by the same number. In this case, it would be 2. So we could get 2/3. If you're at 4 out of 6 in the test, you are not going to get it wrong. This simplification step we'll get better at during the year. And similarly, for the probability of an even number, there's 1, 2, 3 even numbers out of 6. And we could write on the end here, by dividing both of them by 3, that's equal to a half. So half of the time we'd expect to get an even number, and that kind of makes sense. And then we could look on our table up here and say, well, a sixth, where would that be? Down here somewhere, so that's pretty unlikely. We could look at a half, that's in the middle, so that's even chance. And 2/3, that would be up here somewhere, that's a bit better than likely. So now we've got a fairly precise way of describing it against our scale of words. Now, we don't only use fractions, though. We might want to use decimals and percentages based on what the questions asked us to do. So if we took the probability of 2 being a sixth from earlier, to convert it to a decimal, take the numerator and divide the denominator. So 1 divided by 6 would be 0.167 as a decimal. If we wanted that as a percentage, multiply by 100%. And you'll get 16.7. And you'll note that in this step here, all we're doing is moving the decimal point 2 places. So once we have it as a decimal, it's quite easy to change it into a percentage. Excellent. Now, we've looked at what may happen. Let's look at what has happened. So let's pretend for a second that we've done an experiment and we want to get the probabilities from there. In our case, we would probably create a frequency table. Sometimes it has a tally chart in the middle, but in this case, I've just written the frequency table down. So X is where the scores are, and for a coin toss, you'd have heads and tails. And next to it in the frequency column is how often it's happened. So heads happen 5 times, tails happen 7 times, for a total of 12 times. Now we can get the probability of heads based on this experiment by putting the successful trials divided by the number of trials. So the probability of heads would be 5 out of 12. So 5 out of the 12 times we managed to get heads. Now, though the formula is similar for both theoretical and experimental probability, the source of the numbers that we put in are quite different, and we need to be aware of that. Now, the last thing we need to know is about long-run probability and expected values. Now, we can see from our trial over here, the probability for heads in theoretical probability was 1 out of 2, yet the probability for the experiment was 5 out of 12, and that's because random plays a part in experiments. Things happen. Now, what will happen over time, though, is the more experiments you do, the closer the experimental results will come to the theoretical results. Typically easiest to see with decimal values. So if you convert your fractions to decimals, you can see the numbers are quite close. Now, what we can do is we can use the theoretical probability result to predict the experimental result. We knew the experimental result too, but typically it's done with the theoretical result. We take the probability and we multiply it by the number of trials we're going to do, and that will tell us the expected number of trials that we expect to come out of the experiment. So easiest to see with an example. If we're going to do 200 trials and the coin has had probability of 5 out of 12 of getting heads, bit of a biased coin. Out of those 200 trials, how many trials would we expect to be heads? We multiply the probability by the number of trials. That gives us 83.3, so we'd expect about 83 trials to be heads with this coin. Are we likely to get 83 heads? Probably not, because random will still kick in, but it's going to be around about that. Well, I hope that was helpful, and if you've understood all of that, then you are well set for your test. Thank you, everybody.